So for today's lecture, what we'll do is a couple of quick problems. I will not go into everything, the detailed solutions, but we're just going to do a couple of them. Might be a bit short, and then we just go through the overall lecture slides, basically a quick overview of it. And the reason for that is today was actually the exam, so we're not missing, we get basically an extra lecture out of it. And I didn't want to bring up any new topics with the exam coming up on Saturday. So let me open my PDF. I'm going to open the book a bit. So I think we're going to start with let's do problem. This is 6th edition. So for some, if you have the 4th edition, it's also online. Let's just do problem 1, 16.1. I'll draw it out. And the idea is for this, let's just do the finding of the centroid. How to deal with that. And I'll just draw it out on a whiteboard. I'll give you guys 5 minutes to do it, and then we go through the solutions together. So we got basically an angle-shaped geometry. And dimensions are given as 100 millimeters, 10, and another 10 here. And this one is 125. I think in the book they ask you to find, given an you're basically a coordinate system, x and y. This is our centroid. You have to find the centroid, and I think they say assume that you have a distributed load. Let's see what the exact question is. Yeah, bending moment is applied in a plane 30 angles to the vertical y-axis. Okay. So basically they say, well, there's an angle here or axis here that we define, and that one is 30 degrees with respect to the y-axis, and the moment is applied there. So this is approximately 30 degrees. That has 30 degrees, and the moment is 3,000 kilometers. Let me check again. Yeah, 3,000 Newton meter. So let's get started. I'll give you guys 5 minutes. We're not going to do the stresses on this, but this is basically what it is. It's the inverse of what we had earlier. Earlier on the example of last lecture, we had an axis or the moment given on the x-axis, and we had the rotation. Now basically we have on the moment given on rotation, and we have to rotate back to our normal axis system. So what you want to do is you first want to find the centroid, since this is not symmetric, and you want to find the correct moments. And then we're going to stop it there, because after that is just filling in the equation, which is very straightforward. So I'm going to give you guys 5 minutes to solve this. So in first case, this is basically a thick wall structure, also has Tron. So basically take that into account. So I think in a solution manual they take out this point, the reference point, but it doesn't really matter. It can be any point as long as it's remain consistent with respect to finding the centroidal axis. So this is nothing more than the area with respect to the distance to the centroidal axis, and this is the summation of area. So we can do the summation of area. So in this case, this is 100, so we have to subtract this 125, so we have to subtract the thickness. So this basically becomes 115. So have to be careful with that. So the total area, summation of area, is nothing else than 100 times 10 plus 115 times 10, which is 2,150. Millimeters squared. And then let's do the x-axis first. So let's take this as reference. So what's the centroid of our horizontal beam? Basically, centroid will lie in the middle, so we can draw it here. And this will be, by definition, this is in the middle, so this will be 50, and the height, say this section, that will be 5. Now we can draw the same thing for our vertical flange. So we're thinking about this axis here, so the 115, not the 125, so lie in the middle, of course, again. So this part will be 5, just coincidence since both of them are equal thickness, and the top part, or the wide part, will be 115 over 2, so 50, 57.5. And that's from this part, so not from the total part. So if one determine the x distance, which is this, basically we take from the centroidal axis, or from this section, so here to basically to the C location, we call this x bar, and similarly this, that's y bar. So let's fill it in. We take this as a reference. So we have, so x bar is equal to, let's do the top one first, the area, that's 100 times 10, 100 times 10, multiplied by the x bar, that's this location, with respect to its own centroid, that was 5, plus this area, which was 115, times 10, multiplied by its local axis. No, this is not. You have to take the x distance, so that's 50. So that's 50 here, and here towards that reference point, that's 5. And then we divide by the total summation of area, which we said was 2,150. And if you do this correctly, what we get is 25.9 millimeters. So since this is a positive number, and we define positive, we start from here, we all define positive in the x direction, so this means this is 25.9 millimeters away. So we can do the same thing for the y bar. We repeat the same thing, but then we just take the distance towards the y distance from the local centroids. So again, we get 100 times 10. In this case, its centroid with respect to y is 5. That's our reference point, plus 115 times 10, And then this centroid was 75 plus additional 10, so 67.5 over 21150. And in that case, we get 38.4 millimeters. So we are at this location. And you will need this to find the moment of inertia. That basically is the reason why we need this.
Supposed to be 57.5 instead of 67.5.
No, it should be 67.
But
So, sorry?
115 over 2 is. Oh, wait.
Yeah, but then you have to add this part because this is our reference point.
Gotcha.
So you always have to take with respect to your reference point. And thin wall structures, then basically you reduce the thickness, but in this case we don't reduce it. So another point is, okay, let's find our moment. So we have a given moment, and that's 3,000 Newton meters. And always useful is just to convert it to the same unit as how your moment of inertia. So it's 3 to the power 6 Newton millimeters, and that's basically acting in this direction. Now we have to decompose that. So what we have is like this. This is our moment given. This is 30 degrees. So we can just use Pythagoras for it. So this will be your mx component, and this will be your my component. So mx and this one is given. So for mx we use sine 30. Is that correct? That should be sine 30. And this should be cosine 30. Yeah. Let me just double check the correct angles given. So it's 30 degrees with respect to the vertical axis. Yeah, it should be sine and cosine, right? Do you all get that as well? So with sine 30, someone pop that up.
1,500 times 10 to the third Newton millimeters.
And this one, cosine 30?
1,299 times 10 to the third.
1,000.
299. It's 1,200.
Ah, sorry.
I'm sorry.
Not sure why, but Maxon has them opposite. So Maxon has a cosine there and a sine there.
Maybe it's in reference from the x-axis. They're like they took instead of the.
Cos 30 values are different. Double check.
Let me see, I can plug it in Matlob.
Sine of 30 is 1/2, so 1/2 times 20,000, 1.5 makes sense.
No, cos 30 always.
Cos 30 is square root over 2, right? Square root 3 over 2.
3 over 2.
Should be 2600.
I got 2598.
Yeah,
25, 98. So 2.6. Okay, for some reason Maximus ups differently, but I'm pretty sure this is correct. Again, we can draw it again. They say this is angle is 30 degrees. So if this is your moment M, just like forces, you decouple into these two, and X and Y. Let me just think about it for a second. Wait.
that's your left.
It should be sine and cosine.
They could have used 60 degrees from the X instead. Maybe, I don't know.
No, but then the numbers still don't match. I'll have a look into why he chooses the opposite sign. Like I said before, Maxim makes a lot of mistakes, so it can be just an error in it. With that said, what we can do is actually let's continue with doing this problem, and let's do also the moment of inertia, and then we just continue doing this together. Because in this case, if you would, since you have a moment mx and my given, your equation for stresses well, require basically the moment of inertia in all the three directions. So actually, this is not a bad problem to do, because then we use the genetic equation, so we cannot produce anything. Let's calculate the moment of inertia then. I'll go a bit quicker through it. In this case, we assume it's going to be thick-walled, so we take everything into account. So we get the top part, that's basically 112 times 100 times 10 to the power 3, plus this part, we get 112 times, what's that, 115? Yeah, 115 to the power 3 times 10, and then we add the standard terms for both parts to it, because we have to translate it with respect to the coordinates. What we get is, let's do the area first, that's just 100 times 10, and now we have to translate it from 5 to 5 to this was y bar, so from 5 to 38.4, so we basically have to distance 33.4. And the standard term from the other one, the area is 115 times 10, and this will be basically, we start at 60, from this point is 67.5, and we have to go to 33.84, so it's, what is it, 29.1 apparently.
Did you put the cube wrong on the 115?
Sorry?
The cube on the 115.
Yes.
Should it be on 10?
No, because this is a moment of inertia on x. So it's, the equation is 112 h cubed b. So this is the height. So in this case, it will be 115 to the power 3. And in this case, 10 is the height. So that's the reason why it's 10 cubed. So that will be our moment of inertia.
How did you get 29.1?
That's basically, so we get this, the centroid here was at 38.4. So the reference axis here with respect to the top is 67, right? So this comes from 67.5 minus 38.4 squared. That's 21.9. So you translate your centroidal axis, local centroidal axis, towards your cross-sectional centroidal axis. So moment of YY. And basically YY would be slightly as the opposite of this basically. So we get 100 to the power of 3 times 10 over 12 plus 115 times 10 to the power of 3 over 12. And then the standard terms. And now you basically are shifting, instead of Y, you're shifting in X. So again, 100 times 10, that's our area. And then we shift, this location is 50, and centroidal axis was at 25.9, so basically we shift left. So we shift with minus 24.1, but the minus doesn't matter because it's actually squared, so you can just plug in 24.9.1 plus 115 times 10, and then again, our centroidal axis is 5, and we shift towards the right. This was x dash was 25.9, so we shift with 20.9 squared. And then we get moment of inertia on xy. And in that case, it's just basically the area times the shifting of the centroidal axis. So in this case, 100 times 10, and then we have to shift with x and y. So we shift in x, we said that's 24.1.
Explain the 24.1.
Okay. Yeah. So this actually correct. This should be a plus. Let me see. So this is the centroidal axis of the top one, right? And that's from their reference points was 50. Okay. So, and this is our centroidal axis location. So this coordinate system is 25.9, comma 38.4 with respect to this coordinate system. So basically, this is our centroidal axis. So we have to shift this to our correct coordinate system. So we shifted with respect 24.1 to the left.
Okay, 35, 50 minus 35.9.
So you did 29.1 minus 5. So you get 24.1.
No, you do 50 minus 20, 29.1, 25.1, 9. So let's draw it again. So this is our top one, right? This is our cross section. This is our centroidal axis. So this is coordinate system 50. And this is our centroidal axis system. And this coordinate to here, that's 25.9. So we're going from there to there. That difference is 24.9.
And when would it be negative? Because you wrote negative earlier and then you made it a positive. Under what scenario would it be negative?
So in this case, it doesn't matter, but it matters for our x and y.
So you said it's from the local centroid to the actual centroid, is the difference?
Yeah. So we're going from our centroidal axis to basically the centroidal axis where we have it.
So then it should be negative on the second term.
This one?
The second one.
The second, yeah, I got this one incorrect.
Can you explain that one too?
So in that case, let's see here again. So this was 115, right? And this section is, let's draw it here, 110, and this is 115. So the centroid of this 115 by 10 bar lies here in the middle, right? And that's at 57.5. But with respect to our reference axis, where we calculate our centroid, we have to add that 10 to it.
67.
So this reference axis becomes 67.5 from the top. And we know that this axis from the top, that was 38.4.
So 67.5 minus
38.4.
Why is that negative?
In this case, how I would put this as a negative. It doesn't really matter for this case, but the next one we see is how it compares with respect to this axis. This one lies basically, this was your coordinate system, positive x, y, it lies beneath it, so therefore the negative sign.
It's going to be squared, it doesn't matter.
It doesn't matter, for this one it doesn't matter, but now we see the x, y, it does matter.
So, I don't like that.
Why are the values different then for IXX and IXY? Or sorry, IYY. Like, why is one 33.4 and the other's 24.1? Is it just moving what you're subtracting?
So one's from the y direction, the other one's from the x.
Yeah,
Yeah, okay.
and this is your reference axis, right?
Yeah.
So
Right, so if you go to the right of the reference axis
positive,
and left to the negative.
negative, up, positive, down,
So
negative.
it's 38.4.
So this one, yeah, from your centroidal axis. Sorry, not reference axis.
So where did the 67.5 come
That's because we are looking at it based on a reference point.
from? In IXX. If we're taking it with respect to X.
It should be the.
IXX, this central moment of inertia around your x-axis, so you basically take the y distance.
But in the 20.9, we took the x distance. Did we? We did the 50 minus. No. Yeah.
This one?
Yeah.
Yeah. So basically this around x, so you take y distance, this around y, you take x distance. That's
So
So
when
it's
we take
fine.
the x distance, why are we using the 67.5? We shouldn't be using it.
I guess, would a better way to phrase it be distance from X and distance from Y?
It should be 50 minus
which one are you talking about? 1 second.
the IYY first term. The
IYY first term. This one?
Yeah, this one.
Okay. So that's your.
In
Let's
one
see.
term, we are using the x distance, in the second term, we are using the y distance.
No, we're using both x. Let me see. Subtract.
Yeah, you're
So-
saying the arrows are going in the y direction in the 38.4 and the 67.5, not in the x direction. That's what's confusing.
So this is our. Let's draw this. This coordinate system is 38. No, 25.9. 9, comma 38.4. That's our coordinate system. Let's do it just using coordinate systems. That will be easier. This coordinate system, that's 50, comma 5. This coordinate system is 5, comma 67.5. Okay, that would make it a bit easier to understand instead of arrows, yeah. And then you will see those two numbers add up. Yeah.
You still need to extend the 24.1.
So we are subtracting with respect to the x-axis, right?
24.9 is it, or is it
0.9.
1? Oh, yeah, that makes sense.
So because, yeah, so you have 25 minus 5.
Alright, yeah.
Okay. And now it becomes important because now you have your IXY. So like I said, that was area times x distance, y distance. So area first is 100 times 10, and let's actually get rid of this a bit, and then we're going to use just the x and y coordinates as I previously wrote down. So this centroidal axis was at 50,5. This centroidal axis was at 5,67.5. And our centroid was at 25.9, 38.4. So if you look at this, it lies, both of the coordinates basically lay positive to it, so those two numbers become positive. So both the distance towards x and the distance towards y. So what we get is, let me see, 24.1. So that will be 24.1. Yep, that's your x distance. Y distance lays above it, so the difference will be 38 going to 5, so you get 33.4. So that's correct here. And then for the second one is 115 times 10, and then since this one lays to the left and to the bottom, these two numbers will be negative. So what we get is 20.5, 20.9, and we get minus 29.1. So in this case, all three numbers will be positive, but you can imagine that, say, let me come up with a good way. Yeah, so let's imagine instead of around the centroidal axis, we want to take the moment of inertia around this point, for what some reason it is. Then you will see that, well, let's do it around this point. This point. Sorry. In this case, this one will be still positive, and this one will be, one of them is positive, other one is negative, so here you get a plus and a minus. So this actually contribution will decrease it instead of increasing it. So there are examples that the xy component is a negative number, and it becomes, if you don't take into account the correct centroidal axis and the distance towards it, and I think with coordinates will be actually easier than instead of looking at the distance and drawing lines. So you have to be careful with that. That's the only thing that you have to be worried about. And there will be a finer centroid and moment of inertia question on that exam. So
I'm assuming there will be different structures too. So in the case of a different structure, we have to derive the moment of inertia first, and then go ahead and do all this.
Define deriving. So
say you have like, I don't know, a distance, say, thickness T, and then you do like 2AT, and then that would change your moment of inertia.
say this was an this come up with an A problem, right? We have this, and we have a circle, half a circle here, right? And let's do an arc here. So how will you tackle this problem? Just go through the steps.
Well, the length down would be H, and the length to the left.
Let's call this segments 1, 2, 3, 4, and 5.
And I'm assuming at the circle you'd have to take the angle, sine or cosine of that angle.
Not necessarily.
Not sure?
You can. So the first step is, in this case, find the centroid, because your moment of inertia would be focusing on your centroidal axis. Okay? So in this case, step 1, find centroid. So you choose a reference point for yourself. And this is, you can choose this location, you can choose this location, you can choose this location. It doesn't really matter. because at the end of the day, you will get the same central axis location as regardless which position you choose. Your numbers will be different. So if you choose this access point, you might get 10 and 15. But if you choose this one, you might get like -5 and still 15. You get it? So your numbers might be off, but your overall coordinate system will be the same. And often it's just choose a point that's simple. It can be a corner or something that you know. In this case, I would choose this one.
So in this case, you wouldn't still use 112 DH cubed.
Yeah, now you've come up with step 2, and that's the moment of inertia.
So deriving moment of inertia.
You don't have to drop anything in this case, because we know by definition, there's a vertical flanges are given by 112 BH cubed. We know that straights are given by 112 B cubed H, right? And we just fill in the corresponding distances. And if this is thin wall, then if it's a T, then it drops out. Now it becomes this one, right? You can, so what you can do is, yes, you can go make a coordinate transformation. So your y distance, you go to theta, blah, blah, you drive your equation. You say theta is equal, or the y distance is equal to cosine theta. So r cosine theta squared, right? And then you do r dr d theta. That's your coordinate transformation going from your integral basically transforms from y squared dA to r cosine theta squared r dr d theta. But this is already done in literature for you. So your moment of inertia over half a circle, you can just look them up. What does that mean? It also, which you have to take into account, you get a similar thing like this. You will get a equation. I have to think what it was. I think it's YR cubed T. I think it's over 4. Not 100% sure. I think this is it, to be honest. It might be slightly different, but it has a pi in it, has an r cubed in it, and has a t in it.
So
That
if
part
we
I'm
get
sure.
different geometries, we just look at the moment of inertia for those geometries.
Sorry?
So if we get different geometries, we just look up the moment of inertia of those
From the
geometries.
different components, and now you have to come to trick. So you come up with the different components, and this will be with respect to a centroidal axis, say, or the centroid that will be laying there. So now you have to add the Steiner term for that axis coordinate system transformation.
So the question is, if we did look at the moment of inertia, would you take points out where we did not derive the moment of inertia?
No. No. For simple things, no. Unless it specifically asks you to do the integral formulation, I will not drive any points off. And if I were you guys, I would focus on memorizing, because this will not be on the formula sheet, these two and circles. The rest you can either drive very quickly, because that's the only thing what often goes wrong. The half circles, arcs, like 3/4 of a circle, stuff like that. And then you just do the stuff to say if this is based looking on this. Moment of inertia will lie definitely positive y. Yeah, it will lie somewhere here. It will be probably centroid. And then you just translate the coordinates to it. And that's it. And you can solve it that way.
On the exam, would we see anything of that hybrid geometry?
This one, yes. This take-home exam, yes. Final and class exams. Often it's either circles or straight segments with a different angle. Like what we did, there's a problem, the Z section. I think it's that's the actually 16.3. That one was a not recommended problem, but the only reason is because it asks for deflections, but it's good to do that anyways, because you have to find the centroid and then the moment of inertia is for it. Let's do that one actually now. And by the way, it's an open book, open blah blah, so you can use the internet to find the moment of inertias. So it should not be that difficult. I think the basics apply. So we have this example. This is 16.3. This is 4a distance. The height is 3a, and this is 5a, 3, 5. And again, we have to calculate the centroid. Here, so this is y bar. And I think because of, you see, okay, it's assumed, so this one, yeah, this will lie at 2a based on inspection, yeah. So we can do this. Let's calculate the y bar. So the total area, I think everywhere you have a thickness t. So you get 5a times t plus 4a times t, so you get 9a t. Yeah. And then the top, so if you go from this location, what you get is this one. These are reference points because thin wall basically assumes coinciding with each other, so basically 0. So we get only 5a t, and then we basically have to find the y distance towards it. And the y distance from this slanted part will lie here, so at 2.5. Based on geometry, you know it's 3/2. So it's multiplied by 1.5, so 3/2. And of course 3/2a.
Do you explain that one more time?
So you know this is 5, right? Mm-hmm. So the centroid will lie in the middle of it. So we just focus on this individually. And just how this is 4, this is 3. So this is 2.5. This is 1.5. Yeah. 3/2.
Okay, you're saying that 5AT in correlation to the 3A is halfway in between, so that's why it's 3AT?
Yeah. It just figures out from the geometry. It's in the middle. So the height of this section in the middle is a linear, so it goes linearly, so it's 3/2.
And the 9AT is 5A over the added to the 4A, right?
Yeah, so this is 5AT plus 4AT because this is the total area of the full geometry. And we did not have any contribution of this one because we assumed it's thin wall. So you can assume that your reference location and your central axis coincide with each other. So that distance y is t/2, but t is extremely small, so it's 0. Okay. So, and then if you plug this in, so 15/2, so 15 over 9 is 18. We have AT, so that drops. So we get 5 by 3, 506. Yep, 506. So that's our y coordinate.
And we were given x.
You can deduce this 2a. because this will lie in the middle. So this distance is 2a. This will lie in the middle is 2a. So 2. Calculate. You can calculate. It will come up to 2a. From geometry, you can also deduce it. If you're confident on an exam, you can just say based on geometry, you can deduce it's 2a. It's 5 points, and if it's correct, it's 4 points. If it's not correct, it's 0 points. Now you could just calculate. And then based on that, we can calculate the moment of inertia. And we assume a thin wall structure. So let's calculate that. So let's start with the bottom. So basically, you will get 112 times 4a multiplied by t to the power of 3. So that one drops. So we only have that standard term to it. So that's 4at multiplied by y squared. So 5a over 6 squared. So 25 squared over 36. Plus, and in this case, you would do the integral formulation. So y squared dA, y is given by, I think it's 305, you could use that. You see, yeah. Now, you basically go from the integral formulation, so from the centroid, so basically your bonds are negative 2.5a to positive 2.5a, and then 0 to t for the thickness, and then y squared, the y distance is, if this is 4, this is 3, I think by definition this is 30 degrees, right? Yeah. And then you do, say, S times, that's basically your path, times, what is that? Sine 30. Yeah. And you evaluate this integral. So it becomes x as and then of course theta. No, ds. So you get s cubed over 3 sine 30 squared. S is then evaluated from minus 2.5 to plus 2.5. So what you get is 2.5 cubed over 3 minus, then comes a plus 0.5 over 3 cubed, and then sinus 30 squared. So in this case, you use the integral formulation.
Now, I'm not understanding this. So this is a moment of inertia in the x direction, right?
Yeah.
So, okay, 4at plus, and then you squared the 5a to get 25a squared.
Yeah. So this squared.
Okay. That squared.
Yeah. So this is basically 5 over 6a squared.
Okay.
So you get 25 over 36.
And then you get the integral.
So the integral, what you have to do in this case, there's one trick you can do, and I really don't like doing that. I can pull it up on a slide deck. see. Yeah. So there will be your formula sheet given. Let's quickly go to the. Yep. So your standard stuff is given, your moment of inertia, and then at an angle, the simplification that Professor Maxon uses is also given, but I would go and use the integral formulation. Because how he has defined the angles, sometimes you just mess up the angles.
Yeah, so yeah, I'm having a hard time understanding the integral. So you took the integral from.
So you start off with your normal integral, right? So which is the integral of, in this case, y squared dA, right?
Yeah.
So what does the dA part stand for? That stands basically it's a combined integral of dx dy, right? So what is our x coordinates? So we basically have to look at it at a beam at an angle, right? So we have a centroid here because we are calculating with respect to its own centroid. So this is 5a.
Okay.
Let me go back to so people can actually go on with it. So this is 5a. This is centroid lies in the middle, so at 2.5a. So the bounds of the integral for the y distance for this path S, let's call that S, becomes minus 2.5a to plus 2.5a. Because you have to imagine that this is our new axis.
Minus 2.5a plus 2.5a, that's 0. So what is that?
No. That's our bounds of our axis. Integration bounds. It's not a summation.
Okay.
So for the x-axis, it's basically integrating from 0 to t. So for this, we get 0 to t, and the other one we get minus 2.5a to plus 2.5a.
Oh yeah, I thought it said 25.
No, 2.5. And then you have to transform your coordinates from, so y, what is y? Basically, if this is 3a, this was given as 4a. So this angle, theta. So theta is sine theta is given as 3 over 5, or 3a over 5, right?
Yeah. 3 over 5. Yeah.
So yeah, no, just 3 over 5 because a drops.
Yeah, they just cancel.
Yeah. So when you get here, so if you want to basically, when you transform your y coordinate, you basically say that's equal to s times sine theta squared. Y squared is this, right? Now we can substitute, just make our lives a bit easier. We can say that's s squared 3 over 5 squared. So we don't have to deal with the theta. And then, since we did a transformation, we went from y to s. This integral basically comes from, if I now evaluate the x, because it's 0 to t, so it's basically a t, we take t out of the integral. What we get is negative 2.5 to plus 2.5a of s squared 3 over 5 squared ds. And this becomes s over 3 evaluated negative 2.5 plus 2.5a multiplied by t multiplied by 3 over 5 squared. So we know this is a cubed, so minus times minus times minus becomes minus. So when we evaluate in this, basically it compounds because you have a positive minus 3 negatives, so it becomes a plus. Yes.
So if you're calculating the IYY, would it be S cos cosine theta?
Yeah. Yeah. So, and then on the formula sheets, that I just showed you, you have this formula given, so it's called. You just have to be careful how this angle is defined, because this angle is sliding. In this case, we have 30 degrees like this. So it will be basically negative 60 degrees. Right? Yeah, because this angle is defined fast like this. So we have to go like this. So it's basically just that's negative. Yeah, negative 60.
Negative 60?
Yeah.
So that angle seems to be to the right. Why are you getting a negative?
If this would be projected to that one.
So it's a projection?
No, I'm saying if you can apply this formula here, like Ixx is equal to BA over 12 B squared cosine squared phi plus A squared sine squared phi. This phi angle in our example will be negative 60, if I'm correct. Because this is defined like this, right? See how sheet. So this is y, this is your y coordinate transform, this is your x coordinate transform, this is x, and this is how they define phi angle on a formula sheet. So we don't translate to the left or counterclockwise, we translate clockwise with this in order to get that. So our axis looks something like this, right? So now this angle transformation coordinate is,
Oh, since the angle is going clockwise, it's negative.
yeah.
Okay.
Yeah. So then that's the thing I don't like this. So it often becomes confusion which angle to use. Most people that use it tend to make at least once or twice the mistake of using the wrong angle. Or if you just do the integral formulation, especially for slanted section, straight sections, it's very simple.
So if you could figure out the angle somehow, we could use it.
Yeah, you just have to be careful. What I would do if you're going to use that formula sheet, so again, for those online, if you're going to use this formula, be careful on how this angle phi is defined and how it applies to your problem. So that's the only thing that you have to be, yeah. And like I said, in the past, I would say 20% of the people that use this formula use the wrong angle. So 1 out of 5 use the wrong angle.
And what does S represent one more time?
Because you use an integral, so this is this distance, this total distance. If you would say if you start your integration point here, right? So the y distance, the y coordinate changes if you're like here or there. So you use a path as integration path. Okay. I think we have 2 more minutes. Any questions? We only did 2 examples, but I think given, since I know which exam you're going to get, I think it will be useful. Any questions? Any generic comments, requests?
Is there any situations where we would keep y squared instead of changing it to,
No.
using a slant instead of changing it to S?
No. You make your life difficult.
Complicated stuff, Mr. Berzanchi.
Yeah. It's fun. This is the simple part. Okay. So let me think of the exam. Yeah, there's one thing I do want to mention. Let me go make sure it's on. Okay. So, and one of the questions I will ask you to ignore some of the moment of inertias. Just do it. Make your life simpler. Trust me. So, say for example, we had, I think it was one of the examples in the slide deck. So you have a circle like this fuselage, and you want to reinforce it, and we said we can add an eye stiffener to it right here. This eye stiffener has again two components. Has basically 1/12 blah 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 component, right? And has the fact that you have this standard term to it, so the AD part towards this distance right here. So, and this is state you get basically a similar type of problem exam. And how I formulated it is you can basically assume that own contribution of the moment of inertia can be ignored. So that means that this I12 part, say I12, and then this is I to the power 3 for the I beam times the thickness, blah blah blah. This contribution, just ignore that. I've listed specifically in the exam problem. So that's what I mean. It's basically it comes down to the fact that this contribution is so small with respect to this one. It's basically you can neglect that. Yeah, you can use it as a point and just use the standard term only.
That's like the rotational moment of inertia, right? When it's rotating on the sides, when it's the other top surfaces is near zero.
No, it's not. That's nothing to do with rotation. It's just an assumption because the contribution is so small. And I've mentioned it specifically in it, and in the problem that you can ignore it. Please do ignore it because you're going to make your life much more difficult. Else there will be terms like not dropping out and stuff like that. So that's the only thing. Like I said, I've specifically mentioned it in an exam that you can ignore it. Other than that, 3 problems should take you 1.5 hours to solve, something like that.
Is it 3 problems, part A, B, C, D?
Yeah, to Z and then dash part 2. That's 3 problems excluding the appendix, which is 500 pages long. Yeah. No, just 3 problems. The generic problems I could have. Let me see. Like I said in previous lecture, I expect on 2 problems to go one step further, where you basically have to explain what you're seeing on the table. Say, for example, you have to a couple of different cases that you have to fill in using standard formulations, or calculate what the minimum weight is, or what the cheapest option is, and you will see something if you inspect the table and make an observation out of that and give an explanation. I think that's the key part. Other than that is you basically use your simple equation of sigma is moment times distance divided by your moment of inertia. Okay. And then starting next week we'll go into torsion. And if you have any other questions, you can reach me by email. I tend to reply relatively fast. Okay. Thank you, and see you guys next week. Good luck on the exam and the weekend.